station assembly and the wall of EVA taught many lessons to NASA. But even as this work was underway, a new set of tasks had to be addressed by the EVA office: how to maintain the space station.
Well, its station was a very good test bed because in the shuttle era, shuttle flights were relatively short, 7, 10, 14 days. And so if something went wrong, you always had the option to come home, and then you always had the option that, well, we'll just wait and fix that when the shuttle comes back and lands. Well, ISS doesn't land, and so if something breaks, you need to fix it up there in space. And so the EVA role, again, it becomes much more important.
Some of the hardware that's just being launched is just starting its life, where some of it's already been 12 years on orbit and is now getting to that critical juncture where, from a certification standpoint, it might be at the end of the life.
Some of the hardware on the station is critical enough that should it fail, the station would have to be abandoned. To avoid this scenario, NASA identified critical contingency EVAs, spacewalks which could be conducted in short order to fix any failed hardware. Any crew, at any time, would have to be prepared to conduct these emergency EVAs.
What we did was we went through step by step each of those failures and kind of came up with a little packet of a straw man of what your procedures would be, or what your tools were going to be. And by going through that process, we had a situation where one of those items did fail, and we were able to quickly get out the door and go ahead and successfully take care of that problem.
And so EVA becomes an integral part of station operations and station maintenance and repair. And then going to our further exploration destinations, it's even more important, because we're going to Mars. Again, EVA is going to have to play a role in that, because the ship on its halfway to Mars can't come home for repairs. We're going to have to keep it going and do what we can while it's out there in space.
To conduct maintenance EVAs on the station, one assumes the astronauts have a perfectly working spacesuit. A new challenge to overcome in an era of long-term exploration: how to fix a spacesuit in space.
The guys are all suited up. We had a little leak problem with Steve's suit. It ended up being traced to an O-ring on one of the lithium hydroxide canisters we used to scrub the CO2. And,
FR's not really
that is our smoking gun for a leaky suit.
Hopefully that'll get out of the way too.
I can tell you something that really fascinates me is just when we do have a failure of any kind on the EMU, it's kind of like watching a piece of food drop to the ground at a picnic and the ants go get it. That's sort of what happens when we have a failure of something like the EMU, because that's the crew's lifeline. That's what keeps them. It's really our little mini spacecraft, and so that's one of the most important things that we have in EVA. And so when something does go wrong, you see this team come together like those ants and just immediately start working the problem.
Every failure is an opportunity, and sometimes you're forced by necessity to do things that you never thought that you would do.
We had a situation where shortly after the Columbia accident, and we then weren't able to launch anything, we had one of our suits go down. Okay, how are we going to go address this failure? We can't just bring it down now and launch up another one.
The EVA office confronted a first. The only way to have the suit fixed was for the expedition crew to crack open the suit and do the repairs themselves, in orbit, in microgravity, with only the tools already on board.
Because we were going to have to do some things with the EMU that weren't really designed to be done on orbit. They were designed to be done in a lab by technicians, and we were going to have to take pieces out of the EMU that weren't really designed to be taken out.
But when we built this thing in '79, we never would have thought of having a crew member break it open and attempt to fix it. That was just not something that they probably even conceived of.
Ground crews got to work figuring out how to best show the astronauts the procedures for conducting the suit repairs.
After we wrung out all the procedures and got all the steps just the way we liked it, we videotaped it. We shipped it up to the crew, and by having them watch the procedure being done, it helped tremendously.
In addition to learning how to maintain the suit in orbit, The EVA office has also taken great measures learning how to protect it. Working on the station can cause wear and tear on suit gloves.
If that vehicle has sharp edges or pointy surfaces, and then the glove is compromised, a cut glove could be a catastrophic failure. At the very least, it's a critical failure, and you terminate your EVA and you do not accomplish the objectives that caused you to go out the hatch in the first place.
Something we've been doing since the shuttle days, but we have a team of folks that work really closely with the crew, and they go in and they look for sharp edges on any of the surfaces that are going to be exposed to try to avoid getting up on station and accidentally cutting the suit.
We have fixed hardware late in the flow. We file down sharps, we take threads of screws that are protruding through structure and put a cap over the exposed threads so that a crew member doesn't reach behind the structure and cut their finger on those threads. I think the lesson we've learned is sharp edges are very real, and it's crucial in the design phase and in the delivery time frame to verify that your sharp edges don't exist.
Not all sharp edges are fixable on the ground. Some hazards are created simply by the station being exposed to the harshness of space.
EVA, because you're putting a person into a pressure suit that's pure oxygen, that comes with its own unique hazards. And then you put them out into a vacuum. With a space station that is supposed to be designed to not have sharp edges, but has now been out there for some parts of it for almost 15 years, and it's been pulted by micrometeoroids, and we're finding sharp edges on the outside of the station. Handrails and translation pads, we found these little nicks. So that is one area that we have to be concerned about for the future of station is the environment that we're working in. Micrometeoroids could turn parts of the station from an EVA perspective in areas that we don't want to go.
I think we were viewed by the early leadership at the time as a risk. Anytime you go in spaceflight, it's a risk, but then going outside the vehicle is even a bigger risk. And so we were sort of a four-letter word for a while there. In the early days, we did a lot more of demonstrations to show that you could do something with EVA.
Well, it may have been one small step for Neil, but it's a heck of a big leap for me. Copy that, Bruce. Thank you.
And then we were able to demonstrate to the program leadership that we brought to the table an asset that they really needed. We had several missions worth of satellite rescue, where we'd go out and either repair or go grab and put back in the payload bay to refurbished on the ground satellites that had issues. So we kind of made our mark in that regard as well. And so I think that really helped us in the early days to go from something that was to be avoided to an asset that would be utilized.
The EVAs during the early shuttle years would provide valuable experience as NASA began to plan for a new project, building a space station. The mission was to construct a spacecraft the size of a football field, with the work site in Earth orbit. While robots could move the big parts together, the intricate work of connecting cables and other fine tasks could only be done by human hands. The spotlight was about to turn once again to EVA and prompt the formation of an EVA office.
In the early 90s was when we had been developing Station Freedom. But what we began to understand, and what the agency and the center began to understand, was the complexity of the problem or the challenge in assembling what is now the International Space Station. And there was a study, I recall, in the early 90s, the Fisher-Price study.
Our report has indicated that the requirements are significant, but we believe not insurmountable. In the final portion of our report, we have listed a series of recommendations that can be implemented to decrease the total requirements for space station maintenance, encourage the use of multiple systems, such as suited astronauts.
We were heading into this era where we were going to go off and do a significant amount of EVAs to go and build the space station. And the number of EVAs kept growing dramatically.
It was I guess what I'd say, alarming. And so I think we began to understand that we needed to focus on EVA and how were we going to do extravehicular activity in the spacewalks, and how were we going to organize our approach to that.
It was going to take a major step up in our ability to perform EVAs, and so because of that, we started doing kind of sample type of practice EVAs during the shuttle program, where we use some of the types of hardware that we might see on space station to see if it works.
We learned a lot in that era. We learned that it's hard. I mean, assembling things in the vacuum of space is hard, and you have to develop a lot of tools. You have to get worksite stabilization, all those kind of things.
I think that precipitated the formation of an office from headquarters to say, okay, this is going to be so important that we need to go ahead and stand up a specific office to really focus on what it's going to take as a discipline to make sure that these EVAs are successful.
They took that segment out of Space Shuttle, stood at the project office, and then while the work may still be working in engineering or space and life sciences, the authority went through the EVA project office.
I think what happened is basically the management took ownership of EVA, and we kind of forced it upon both shuttle and station, who were our customers at the time, to do trades, to go off and acknowledge the risk associated with EVA and compare that to the required design changes for all aspects of the development of the space station. Do you want to go and develop in the design change, or do you want to have to go and do 2 or 3 additional EVAs with the risk associated with doing those EVAs?
Not just thinking about, okay, I've got to build a piece of hardware, but how's that piece of hardware, that tool, going to interface with a piece of station hardware? Not only that interface, but that task, how long is that going to take? How does that interact and play with the capability of the tools and the suit, and what impacts does it have on the station program? What do they need to account for? What changes perhaps do they need to make in their hardware design? All that now centralized and focused in one organization. I think it helped with the communication and with the planning and the integration.
The design of the space station evolved into the International Space Station. But one concept remained the same. Station assembly was going to rely heavily on spacewalking astronauts. This spike in EVA activity became known as the Wall of EVA. One of the first questions the EVA office would address was what those astronauts would be wearing for the assembly tasks.
Starting with Space Station Freedom, and then later for the International Space Station, the thought was, hey, just like for Apollo, just like we did for Shuttle, just like for Gemini, they each had their own spacesuit. And so the thought was, hey, let's go build a new spacesuit. And obviously budget cuts begin to happen. And so for whatever reason, the decision was made that EMU would be good enough.
So as station came into focus, the EMU system was getting close to its design limits, 15 years.
And when you got to those years in 92, 93, 94, 95, and you began to look at the systems, well, they weren't used as much as they expected. And the reality was, at the end of 15 years, metal doesn't just suddenly turn to dust. And so we set about a program called Assured EMU Availability. How are we going to assure that the EMUs are available now for station and to complete station assembly?
We did not go out and build a new spacesuit, and I think a lot of people that probably don't recognize that. This is essentially, the suit we use today is the same suit that was designed in 1979. We've made some enhancements, but for the most part, it's the exact same suit. And so there were a lot of things that we've done, trying to make it a little bit better.
The current configuration suit is almost 30 years old, the way it looks, but underneath the covering, from all the lessons learned, there's a lot of differences.
We changed out some of the components from aluminum to stainless steel, which lasts a lot longer and much more easy to refurbish on the ground. We added some components where things were needed, upgraded the technology in the electronics world especially. Nobody has a computer that's 40 years old on their desktop.
And so we went through a series of redesigns with the gloves, trying to make them more mobile, give you better dexterity, ease the physical burden on the astronaut and being able to manipulate the indices of his hand. and adding something to protect against the thermal extremes. And so we added some heaters in the gloves as well.
Yeah, a lot of credit goes to the early designers and developers of that 70s era technology spacesuit. They built into it a lot of margin that we are living on today.
You never know when you build a piece of hardware. The guys back in the 70s and gals that built and designed and tested the original EMUs, you never know where that hardware is going to end up, and you never know how it's going to be used. So when you write your requirements and you design your hardware, remember that it may be used in an environment you never anticipated it being used in.
While the suit was upgraded, the EVA office prepared for station assembly in other ways. One key to mission success was to be involved with the design of the station hardware the astronauts would be handling.
I think Space Station is an excellent example of how EVA was involved early and often in the design of the vehicle. We, NASA, understood going into the Space Station program that there was going to be this wall of EVAs. We were going to need hours of EVA crew member time to build the space station. Because we knew that going in, the vehicle was designed for that work to occur safely and successfully. There are translation paths to the work sites. The connectors and the cables that the EVA crew members had to plug in from element to element as each of them were attached. Those connectors were designed to be handled and operated by crew members. We tested it. We found some of the hiccups in the design and then built tools to help the EVA crew members actuate whatever that mechanism was that wasn't as easy as had originally been conceived. So Space Station benefited because they planned for EVA to be a critical part of the assembly.
Station assembly was underway, with EVA taking on their tasks mission by mission. The most complex engineering feat conducted in space, the construction of the station, was bound to have its challenges. To overcome problems, the EVA office worked together with other teams.
A lot of EVAs we run into off-nominal situations, and sometimes it just takes a little more effort on the part of the crew member and the ground to overcome it, and sometimes we stop and we come inside and we think about it, and then we go out another EVA and we tackle it again.
On STS-97, there was which was the Station Assembly 4A flight, there was a problem with the deployment of the solar arrays. And so they put a small team of us, and it consisted of people from the EVA office, from MOD, from the crew office, from engineering, from safety, and a struck and mech representative. Nobody was worried about what organization each other was from. Nobody was worried about what badge we were wearing. And that's not the only time that happens. That happens, countless times over the ISS assembly.
We try to always think about what can go wrong, but there's probably infinite number of things that can go wrong. But when these things do go wrong, we pull in these teams in real time.
If you think back to kind of the Apollo 13 movie, throwing everything on the table that's available for them to use. And, that kind of stuff really happens. And so you have all these different people with a common goal, but totally different perspectives coming together.
Back, I believe it was STS-120, well, as they reopened one solar array, the array became stuck. It tore part of the array. And we never thought we would go do EVAs on the solar arrays. It's an area that has a lot of electrical conductivity. It's hazardous, it's a shock hazard for the crew member. We never thought we would do it. In a very short period of time, we sent him up on the arm, on the boom, with tools that had been Kapton taped over, and we went and we repaired the array, and we did that pretty quick.
We've had, on the order of over 100 EVAs to assemble a space station, in some years 20 or more EVAs, and there's no way we could have done that without all these organizations working together as well as they did.
That's really the fun part of the job. That's the fun part of the job, is when you fly in space and things don't work like you thought they should, and then you've got to very quickly as a team come together and solve the problem.
It is the early 1980s, and NASA has a new spacecraft called the Space Shuttle, which is getting ready for its maiden voyage. A new program gets a new suit, and technicians eagerly ready the shuttle spacesuit for human testing. They're about to discover that for EVA, lessons learned can begin long before a mission ever launches.
It was in the early 80s, and the program was still kind of at the development phase. We had not gone through certification yet. We hadn't flown the first shuttle flight yet. So we were still building and learning about this spacecraft called the EMU. One day we were testing the spacesuit the first time with oxygen. It was getting ready for a human test later in the week.
And this test was to turn on the SOP, which is the secondary oxygen bottles. As we got to the point to throw the manual switch to the SOP, or the EVA position is what they call it, at that time, the technician was over the top of it. He moved the switch.
We had a flash fire, and it consumed the suit, severely injured one of the technicians who was right next to the suit.
One of our lessons learned is that we hit where we had the test stand situated. It didn't allow for a good egress, so everyone ran to the back side of the test stand. Myself, I happened to be on the opposite side, so I had good egress to the door, and I made it to the door and got out, got a fire extinguisher. By then other people were coming, and we started to put the fire out and then get the rest of our people out.
And it was determined that a very small piece of metal, about the size 8/1000ths of an inch, when it's accelerated in the oxygen flow stream, could create this kind of event. And so that made a big impression on me and a lot of the younger guys in the engineering ranks at the time, that something that small can't be overlooked. And so that framed a lot of our decision making going forward.
The investigation brought a lot of good things up. Nowadays we have processes where we buy off a block, or the quality person will buy off a step, so you have this check and balances. Those are really good processes that have been put in place. Bring in that outside set of eyes to look at your hardware, get that second opinion of something.
If we don't do this right, the end user, who a lot of times are sitting in meetings with us, or friends, or we see them at the grocery store, might pay that ultimate price.
When you're going and looking at your project or your task at hand, look at the hardware and look at the people. We all want to go home at the end of the day healthy and safe, and that's our priority here. Yeah, I do have a quote that I would like to pass on to everybody, and this is by Winston Churchill, and it says, "All men make mistakes, but only wise men learn from their mistakes." I think those are some good words to go forward with.